All right, well, let's look at some examples of operations on a heap. So let's say we have this heap and we want to insert the number 7. Where should it go? Well, it helps to no longer picture this in the tree form, but let's look at it back in the array form. We'll look at it in both ways, actually, the tree form and the array form. As you can see, it doesn't really make sense to try to wedge it anywhere sort of inside here. Also doesn't make sense to put it way out here or anywhere. So really the most natural place to put it is here at the end, which means to put it as a child of this 4. So right here. So we'll always put it in the next available slot. And the reason for that is we don't want gaps in the array. They're going to signal the end of a search if we're sort of moving up and down the tree. So for example, if we come to this 4, we go to the 8, we go from the 8 to the 12. If we see that the 12 has no child to the left, we're just going to assume that there's nothing that's a child of that sort of invisible node, and that there's also nothing to the right of it. We're always going to assume that we have what's called a complete tree. So we'll put the 7 at the very end. And then we check the heap property, and the 7 is greater than or equal to the 4, so we're done there. How about inserting a 10? Again, we'll just put it at the next available slot, which is to the as the right child of the 4. And then what happens next if we want to insert a 5? We do the same thing. We always put it as the last available slot, which is the left child of the number 12. I know my arrows are a little deceiving here, but that's the left child of the number 12. And now we've got a problem. We've violated the heap index, the heap property. And how do we know we've done that? Well, in constant time, we can say, I know the index of this lastmost element. You can compute that just by saying what's the length of the array, and that would be the index of where you put the most current element. And you can get the index of the parent element, which is the 12, in constant time. So we can do that comparison in constant time. It doesn't take much work. And we know that the 5 is less than the 12, which doesn't work according to the heap property. So what we do is we just swap them. And now we should be in a better spot. And now we just do the same thing again. We know the index of the 5 because we just swapped it into that spot. And we compare it to the index of its parent, which is this 8. And we have another heap violation, so we do another swap. And now we can do the same comparison again. We know the index of the 5 and the index of the parent, and now we're no longer violating the heap property, so we can just end it there and leave the node 5 where it currently exists. What is your best guess for the running time of this operation? In the worst case, we have to move from the bottom of the tree all the way up to the top of the tree. Well, we know that a binary tree has a logarithmic height. So the height of this thing is actually going to be log of n plus 1. And that means that this operation has a big old log n running time. Because at each one of those places in the tree, each of those levels in the tree, the height of the tree is just log n. The levels start at 0, 1, and go on. I think I do that backwards. This is log of n plus 1. Sorry for that. Yeah, so we're doing a constant amount of work at each level in the tree with log of n levels. All right, so that's an insert. Oh, yeah. And this is usually called bubbling up. So you have a node, and it has to get bubbled up the tree. How about the next operation we support for heaps, which is to extract the min? Well, we know the min is right here, and we can access the min in constant time. We know the index of the min is always sort of the leftmost part of the array. But how about actually extracting it? What does that look like, and what will be the running time? Well, to extract it, we need to replace the node 4 with something. So I'll put a pause in the video here, and I just want you to think about what are our sort of most likely options for replacing the 4. Well, one common suggestion is to replace it with the smaller of its 2 children. So what if we do choose a child? Okay, well that would be the 4. So we would pick the 4. Why wouldn't we pick the 5? Well, if we move the 5 up, then we immediately have a 5 here and a heap violation between those 2 values. So we'll definitely take the smaller of the 2 children. That does make sense. And then we have a gap here, and we don't want a gap because that would signal that this heap only had 1 element, because we'd start at the root and we'd see that there's nothing to its left, which means we have this gap, and we would just end it there. Well, what do we replace that gap with? Well, you might think, again, we'll just replace it with the smaller of its two elements, and so on. Well, what do I now put in this gap here, which shows up here? Where there's no guarantee that this value over here could just be plopped over. And if we moved anything else to there, we'd have another gap. So we might have to do the work of moving that over and then having it bubble up the tree again. So that would work. It's just sort of more work than we need to do. If we're going to have to potentially do some bubbling with this value anyway, it turns out that it's better just to start with that value, and we'll end up doing less work on average. So instead of doing the replacement with one of the children, we're just going to replace it with this value over here because we are guaranteed that that's never going to create a gap anywhere in the array. So we take the 4 out and we replace it with the last element in the array. And at that point, we're almost all but guaranteed to have to do some bubbling down. But like I said, it still on average turns out to be less work overall. So now using the left children equations, we can compare the 12 to its 2 children, replace it with the smaller, and replace the 12 with its 4. And then look at the 12's 2 children and see if there are heap violations there. They're both violating, so we replace it with the smaller of its 2 children, and then so on all the way down the tree. And we usually call that bubbling down. All right, so if a bubbling up operation was big O of log n, it turns out that a bubbling down is also going to be big O of log n. So an extract min is going to be big O of log n for the same reasons that an insert was